Over the past 6 decades, lasers and laser-based devices have become indispensable in many areas of society. With its long-range narrow beam that can be focused into a tiny spot, a laser provides high power over a small area. And this is, of course, useful for cutting, drilling, welding, but not only that, it's also useful for laser surgery and laser skin treatment. The laser is truly one of the many examples of how so-called blue sky discovery in fundamental science eventually may transform our daily lives. The Nobel Prize in Physics for 2018 has been awarded for groundbreaking inventions in the field of laser physics to Arthur Ashkin, Gérard Mourou, and Donna Strickland. And all of these three will be giving talks. Unfortunately, Dr. Ashkin will be giving a talk by proxy, but nevertheless sends a greeting. Arthur Ashkin is an American physicist born in September 1922 in Brooklyn, New York. As an undergraduate at Columbia during the Second World War, he worked part-time at the Columbia Radiation Lab, building magnetrons for the US military radar systems. Receiving a BA in 1947, Ashkin moved to Cornell. Here he studied nuclear physics for a doctoral degree, deciding in the end not to pursue a career in this field where his older brother, Julius, already was a renowned scientist participating in the Manhattan Project. Obtaining a PhD in 1952 from Cornell University, Ashkin got an invitation from his former supervisor at Columbia, Sid Millman, to join the Bell Labs and started working there, researching microwaves before switching to lasers. He was the head of the Department of Laser Science at Bell Labs, Holmdel, for over 20 years, from 1963 to 1987, from time to time also filling in as a member of the technical staff. Ashkin's dream was to trap and manipulate atoms. And in 1986, he and his colleague Stephen Chu, Nobel laureate 1997, demonstrated the first stable optical atom trap, later known as optical tweezers. Ashkin then focused on developing the tweezers to capture and study living things, like bacteria, algae, red blood cells, without harming them. His success has a huge impact on biological research, allowing, for instance, to study how infectious organisms attack healthy cells. Although still active, unfortunately, as I said before, Dr. Ashkin cannot be with us today. He sends a greeting, though, and a close associate, Dr. René Jean Essiambre, who will give the talk in his stead. And so I invite Dr. Essiambre to join me on stage.
I'm Arthur Ashkin. I want to thank the Royal Academy of Sciences for the great honor of a Nobel Prize. And you know I can't be here for when the time comes, but my friend Rene, who's a fellow Bell Labs man, very good friend, he's going to deliver the lecture in my place. And, well, okay, I hope you enjoy it. Thank you.
So it is a great pleasure to be here today to deliver the 2018 Physics Nobel Prize lecture of Arthur Ashkin. As you just saw on the video, we prepared the presentation together, and it reflects what he wanted to discuss today. So this lecture is on optical tweezers and the application to biological systems. First, I will present a few historical events that shows that our art was interested by the action of light from a very young age. Then I will talk about the early days of optical trapping, light pressure, the origin of laser trapping, optical levitation. And then I will discuss the work that was recognized by the Nobel Committee, optical tweezers, laser trapping of biological particles, and then biological application of optical tweezers. In 1932, Art was 10 years old, and he was fascinated by the Crookes radiometer. So a Crookes radiometer is, it looks like this. It's 4 vanes that are linked together and suspended on the pinwheel. Each of the vanes have a dark side, a black side, and the other side is highly reflective, like act as a mirror. And all of that is within the glass bulb with partial vacuum. So when light shines on a Crookes radiometer, the black side starts to move away from the light, so it starts to move in this clockwise direction here. So the Crookes radiometer is moving due to thermal effects. In 1944, when Art was 22 years old, 22 years old, he was working on the pulse magnetron, like was mentioned earlier. He was at the Columbia Radiation Lab. So he decided one day to shine this magnetron to the diaphragm of a phone earpiece. And the magnetron was operating at 1 kilohertz, and he saw a 1 kilohertz trace on the oscilloscope. At the time, he thought it could be radiation pressure. In 1966, a few years after the laser was invented and demonstrated, Art went to a conference in Phoenix, Arizona, where he saw a video by Rawson. And in the video, you would see the particle inside the laser, in the internal beam of the laser, to start to move in straight line and bounce around. And at the time, the authors, Ranson and May, suggested that it could be a few different things. One was light pressure, the other one was thermal effects. So Art calculated what the light pressure will do and figured out that it could not be light pressure. So after a few months, everybody settled to say that it is thermal effect. But the main impact of this video on Art is to reignite his interest in light pressure. So what is light pressure? So let's consider 2 different types of objects. A metallic mirror that is highly reflective, and a transparent small sphere. So when a photon comes and hits the mirror, if it's a tiny mirror, it's going to start to move in the opposite direction to conserve the momentum as the photon has been reflected and the mirror goes in the other direction. For a power of 1 watt, this corresponds to a force of 10 minus 8 Newton, which may appear extremely small. But let's look at a transparent sphere that is 1 micron in diameter, so it's very small. So if we shine light on it, let's say we have a photon that arrives at the upper part, is deflected downwards, and the sphere will start to move upwards in reaction to the photon changing its direction so that the momentum is conserved. If the photon arrives in the lower part of the sphere, it's deflected upward and the sphere goes downwards. So this is the basic mechanism for trapping. If you have 2 photons going symmetrically located, the small sphere will go forward. For a power of 1 watt on 1 micron sphere, the acceleration it can induce on the sphere is on the order of 100,000 times the force of gravity. So the radiation pressure that appeared to be very small on a very small object like a transparent sphere can produce tremendous accelerations. So now let's consider what happens if the sphere is not exactly on the axis of the laser as it was in the previous slide, but now is half axis. So what will happen to that sphere, the transparent sphere? So the laser has, of course, higher intensity near the center, and the laser goes in that direction, and lower intensity at the edges. So as we saw in the previous animation, if a photon arrives on the upper part of the sphere, it will be deflected, and there will be a force on the sphere. If the photon arrives at the lower part, the force in the other direction on the sphere. So that the sum of the force can be decomposed into two forces: the scattering force, which makes the sphere move in the direction of the beam, a gradient force that makes the sphere go toward the center of the beam. So what is very interesting here is that the sphere will be attracted to the high power region of the laser, which seems a little bit counterintuitive, but it actually happens. So the sphere goes towards the center of the beam. So let's look at a little animation. So the photons are arriving here, more photon at the top because it's near the center, less photon here, and the ball will start to move toward the center of the beam. When it's at the center, it just moves forward to the scattering force. And here it's going to hit a microscope slide that stops the sphere. So the sphere is trapped by the beam on the left and by the microscope slide on the right. So Art got the idea that, because he saw this phenomenon, that he could actually put two beams counterpropagating and put a sphere in the middle, a transparent sphere, and this sphere will be trapped because the scattering force of this beam and the scattering force of this beam will compensate each other, and the particle will be in equilibrium there. So that's part of his notebook in 1969. And this notebook was signed by Eric Ippen and Peter Wolf, two famous scientists on their own, and signed by Arthur Ashkin on September 8. So here's a little animation on this two-beam trap. So all the photons arrive symmetrically, so the net force on the sphere is 0 and doesn't move. So this is the first all-optical trap. So Art decided in the next year, in 1971, to look at what will happen if he takes the laser and turn it upwards and use gravity as a force to produce a trapping. So here's the laser. So initially, the sphere is sitting on microscope slide. Then we turn on the laser, but it's too low power. The sphere is not levitating. We increase the power, more photons, and the sphere will start to levitate. And eventually, this at a height that is determined by the laser power and the beam divergence. So Art decided that he would try to measure the charge of the electron using an optical levitator. So here's the setup. That was in 1980. So there is a sphere that is levitating, and there is a feedback control where he's monitoring the height of that sphere, and it changes the power of the laser to keep the height the same. So then he shined UV light in the chamber. That created electrons, and he applied difference of voltage, something similar to the Millikan experiment. So the sphere started to acquire charges, and the power of the laser it's adjusted automatically to compensate the electric force that the sphere will undergo under this difference of potential. So here are the measurements. So you can see that this is the charging time. So how long the UV light is on, and this is the power of the laser needed to levitate. And you can see as the UV light shines and charges are created on the sphere, the power to levitate changes. And of course, it's actually step exactly by the power, by the charge of the electron. It's a discrete power change that corresponds to the charge of the electron. And this is a very high accuracy measurement of the electron charge using optical levitators. Now, let's talk about optical tweezers. The term optical tweezers has been coined by Art himself, and he has been rewarded for the Nobel Prize for this work. So, what is optical tweezers? So, a laser here that goes to a high numerical aperture microscope objective, focus the light very tightly, just not too far from the objective. And what happened is that if we look here at a zoom on this location, at the center here, the minimum size of the beam, the waist of the beam, the highest power is in the middle here. Then there is a gradient in the transverse direction that any laser has. It has more power near the center of the beam than on the edges. But now, because of this very tight focusing, there is a gradient of power along the axis of the beam. So now, from the center here to going forward, there is a very big gradient of power. And what is the impact of that? So we have learned from previous slides that a sphere is attracted towards the region of high power. So the sphere will experience a force that's called a gradient force that is not forward, but is backward. So the sphere wants to go back to the center of the laser. And if you have a sufficient focusing, then the gradient force will exceed the scattering force that is always there and produce and attract a small sphere towards the center of the beam, but not exactly at the center. There's a little bit offset where there's a maximum gradient of the light. So the sphere will settle just before the focus. So in a single beam, you can trap a small spherical transparent particle. So let's see it in operation. So here we have an optical levitator, which will be used just to bring the spheres next to the tweezers. On top, you have the optical tweezers. So the sphere is at the bottom of the tank. We turn the laser on. So the tweezer here is a fixed power, very high intensity near the focus point. Then there is low intensity of the levitator. It's not sufficient to levitate. Then we increase the power of the levitator. The particle goes up, and then it's trapped. So a particle, let's do it again. So when the particle lifts, it becomes trapped all of a sudden at this location just after the focus. So that's the way an optical tweezers works. So let's now talk about some of the biological application that Art himself measured. So in 1987, Art and Joe Jejits, his technical assistant, set up a microscope to trap bacteria using a 1.06 micron neodymium YAG laser. So he started with non-living organisms and something that doesn't have the shape of a sphere. So here, I'm going to show a video that he took himself, where you can see this irregular particle being moved by an optical tweezer. And you can see, obviously, that it's not circular, but it's going to be manipulated by the optical tweezers. So the laser is at 1 micron, so we cannot see. It's not visible. But when it's turned on, it moves this small object here. So it shows that you don't need a sphere to use optical tweezers to exert force on objects. Then he turns his attention to living organisms. So here's a paramecium. A paramecium is a single-cell organism. It is between 50 and 330 microns, so it's fairly big. It has internal component called organelles, and they range from a few microns to a few tens of microns. Here's a video that Art took where he trapped one of the organelles. So I want to attract your attention here to the white dot, which is an organelle. And he's going to trap the organelle twice. So let's look at the video. So this organelle is trapped, and the paramecium will move. And then when the organelle hits the wall, it's exit the trap, and it's going to be trapped again. And when it hits the wall, it's leave the trap again. And now, let's look at what happens to a tobacco mosaic virus. A tobacco mosaic virus is very long, so it's very different from a sphere. So I want to attract your attention here, this rectangle. So the tobacco mosaic virus is free, it's moving around. Then it's going to be trapped. So now it's trapped, doesn't move. And then it's turned inwards. And because it's trapped using by the end of the virus, because the end of the virus refracts light more, and the optical tweezers is stronger. And now, Art decided to trap spermatozoan, and we can listen to him describing what he's doing. This is 1988.
The trap may not, I don't know, the power may not be high enough, or he's too active. Here, let me put up, I'll give you, well, this is about the maximum power.
Let's see if we get it.
Here, let me see, here, I'm moving him. Now I got a reference to move him, right? Mm-hmm. Here you can see I'm moving him. Mm-hmm. So that's working.
So now let's talk about a few different applications. So molecular motors are biological molecules, molecular machines that are the essential agent of movement in living organisms. So here's an example of the kinesin. The kinesin is a molecular motor that can carry a load. Here, a bead has been attached to a kinesin, and the kinesin is on a microtubule. So the kinesin wants to transport that bead, and that bead is being trapped by an optical tweezer. And this optical tweezer is soft in the sense that it traps the bead, but not too strongly. So the bead is kind of free to move a little bit, and as it moves, it deflects the beam of the tweezer, so it can be detected where the bead is in the tweezer. And if we look now at measurements, those are three different measurements. The step size here, this is a function of time of the position of the bead, and you can see the bead move, and by step size of 8 nanometers. So the bead is kind of, the kinesin is kind of walking along the microtubule. So it's making an 8 nanometer step, stop for a while, another nanometer step, and so on. So now let's look now at something a little bit more advanced, which is the measurement of the DNA on DNA templates. So a DNA template is attached to one bead, which is in a trap. Then the RNA polymerase is attached to another bead, also in a trap. One of the trap is soft, so it lets the bead move. The other one is strong. The bead doesn't move much or at all. And what we're going to observe here is that the NRA polymerase is transcribing the DNA. And we're going to see a video that is at 30 times the speed of the two beads moving from a single DNA and single RNA polymerase in action. So the bead is moving, as you can see. And what brings them together is the RNA polymerase transcription. So now, if we look at the measurements of this distance between the beads, this is a measurement that is about 1200 seconds. So we can zoom on it because it has a very high resolution by a factor of 10. So we see how sometimes there's no motion, sometimes there is motion. And if we zoom even further, we can see that now there are steps of 3.4 Armstrong. So 3.4 Armstrong is only a few atoms wide. And this 3.4 Armstrong corresponds to the distance between the nucleotides of the DNA. There are other applications also of tweezers. Here are some: biopolymers properties, motion and forces of linear and rotary molecular motors, molecular behaviors of nucleic acid enzymes, folding of structured nucleic acid and proteins, protein binding, and micromanipulation of small objects in general, and probably many more to come. There are also several companies selling optical tweezers for different applications and different types of tweezers. Art also wrote a book in 2006, published in 2006. He wrote it with the help of his assistant of his wife, Aline, where he presents the fundamental of optical trapping. It discusses different biological applications of optical tweezers. It's also an historical account of the development of optical trapping around the world, but also at Bell Lab. So here are some of the people closest to him. Joe Jejic, with whom he worked for many decades. His wife of 64 years, Aline, and some of his closest collaborators over the years. Thank you.